I'm starting with module number 1. So I'm just showing you the syllabus part of it. Here you can see measurement of resistance, measurement of inductance and capacitance. So in measurement of resistance, we have Wheatstone's bridge, where we can measure the resistance of medium range. We'll be studying about sensitivity of Wheatstone bridge, limitations of Wheatstone bridge. Then we'll be talking about Kelvin's double bridge for the measurement of low resistance. Then earth resistance measurement by fall of potential method and by using Megger. We'll be using this Megger for measuring high resistance. So for medium resistance Wheatstone bridge, low resistance Kelvin's double bridge, and high resistance we'll be using Megger. Then the next part of module 1 will be measurement of inductance and capacitance, where you'll be studying about sources and detectors that you'll be using in AC bridges. Then Maxwell's inductance and capacitance bridge for the measurement of inductance. Hayes bridge, this is another bridge circuit for the measurement of inductance. Anderson's bridge, and then you'll be studying about de Sauty's bridge and shearing bridge for the measurement of capacitance. At last, you'll be studying about shielding of bridges, and finally problems. So this is what we'll be dealing in module number 1. So our focus will be measurement of resistance, inductance and capacitance. We'll be studying about measurement of passive elements. So far in the earlier modules, module number 3, 4 and 5, we have studied about extension of instrument ranges, measurement of current, voltage, and we have also seen measurement of flux density, magnetization force, leakage factor, and we have also seen electronic and digital instruments, display devices, recording devices, etc. So here we'll be talking about measurement of resistance, inductance and capacitance. So today we'll be starting with measurement of resistance. So coming to measurement of resistance, see, generally when we try to measure resistance, we'll be using something called as bridge circuits, and also we'll be using instruments. So let us see what is a bridge circuit, and then we'll also study about instruments like Megger. So before starting about the measurement of resistance, we should know the range of resistance that you're going to measure. Whenever the resistance happens to be lesser than or equal to 1 ohm, it is categorized under low resistance. Whenever the resistance falls in the range between 1 ohm to 0.1 mega ohm, it is medium range resistance. And whenever the resistance range is higher than 0.1 mega ohms, it is coming under high resistance. So we have different circuits for measuring low resistance, medium resistance and high resistance. So first let us understand what is a bridge circuit. So whenever you're having 4 resistances connected end to end with a detector connected across the 2 opposite junctions and source voltage applied between the other 2 junctions, it is called as a bridge circuit. So please have a look at this diagram below. This is basically a bridge circuit. So let us see bit by bit here. Bridge circuit definition: 4 resistors connected end to end. So here you can see RA, RB, RC and RD are connected end to end. See, one end of RA is connected to other end of RB. RB second end is connected to RC. RC other end is connected to RD, and other end of RD is connected to RA. So end to end connectivity is there. Then next line, with a detector connected across 2 opposite junctions. So here whenever you have connected 4 resistors end to end, you will have 2 junctions. I'm showing you, just have a look. This is one junction, this is the other junction, and here you are having 4 junctions are there. So between RA and RB you are having 1 junction, between RC and RD 1 junction, between RA and RD another junction, between RB and RC another junction. So here a detector is connected across 2 opposite junctions. So we are going to connect detector. This G, whatever you are seeing, which is a galvanometer, this is nothing but a detector. The name is called detector because it is going to detect whether the bridge is balanced or not. So this detector is connected across 2 opposite junctions. And then let us continue. And source voltage applied between the other 2 junctions. So you can see here the junction between RA and RD, RB and RC it is connected to battery E or source voltage E. So this defines the bridge circuit. So whenever the circuit is to be called as a bridge circuit, there should be four resistors connected end to end. But in one opposite pair junction, you should have a detector. In the other pair, you should have a source or uh, a battery. Then it is called as a bridge circuit. And the bridge circuits that we are going to use for measurement of resistance is called as basically a DC bridge circuit, because the source voltage is always DC. And when we go for measurement of inductance and capacitance, since they are frequency dependent elements, we'll be going for AC source, so they'll be called as AC bridge circuits. So here these circuits for measurement of resistance are called as DC bridge circuit, as the source is DC. Now let us take up the next definition, that is bridge balance. This is very, very important. So whenever you have applied the voltage E and some known current I is passing through the circuit, if the galvanometer present here reads 0, then the bridge is said to be balanced. So there is a galvanometer connected between these two junctions. Whenever this galvanometer reads 0 for a particular current, then we say the bridge is balanced. So this basically works on null deflection principle. Already we have seen an instrument also in module 5 which works on null detection principle. Here also it's the same. Whenever there is no current going to flow through the galvanometer basically shows 0. Then the bridge is said to be balanced. So this is what is called as bridge balance. So we have understood what is bridge circuit, and then we have understood what is bridge balance. Next. Now we start with the first circuit, which is called as Wheatstone bridge circuit. So this is basically used for the measurement of medium range resistance, which is between 0.1 mega ohm and 1 mega ohm. So this is called as 1 ohm to 0.1 mega ohm. Measurement of resistance falling in the range between 1 ohm to 0.1 mega ohm. So we have this Wheatstone bridge circuit. I have all the four arms here, R1, R2, RS, RX, and I have source voltage E. Current flowing is I. Here in this Wheatstone bridge, R1 and R2 are called as ratio arms. The name for these two resistances are ratio arms. RS is nothing but the standard resistance. Rx is the unknown resistance. The unknown resistance of medium range that you want to measure will be connected between A and D. At this position it will be connected. R1 and R2 will be known to us. RS standard resistance also will be known to us. Only Rx is unknown resistance that you want to measure. And source voltage E also will be known. So ratio arms, standard resistance, unknown resistance, applied voltage E, capital I is the current. And you very well know, as per KCL, current gets divided at node A. Here you are having four nodes A, B, C and D. Current I is passing from the source, which gets divided here, and the current through the branch R1 is named as I1. Current flowing through the branch Rx is named as I2. Current flowing through R2 is named as I3, and then current flowing through Rs is named as I4. So you are having I1, I2, I3 and I4. So now let us derive the bridge balance condition. We already said that bridge is said to be balanced when current flowing through the galvanometer is 0. When the current flowing through the galvanometer is 0, bridge is said to be balanced. So we'll have to derive a condition for that. Okay, let us start with this. When bridge is balanced, no current flows through the galvanometer. So Ig, if we take it as galvanometer current, it should be 0. Whenever the current flowing through this galvanometer is 0, potential at B and D will be same, or the potential difference will be 0. You very well know that current flows only when there is a potential difference. If the potential at both the ends are same, no current is going to flow. So already we know that at balance condition, no current is going to flow. So if you take that into consideration, voltage at B and voltage at D will be same. Or if you consider the potential difference VB minus VD, it will be 0. So it is written as VBD is equal to 0. Now let us apply Kirchhoff's voltage law in loop ABDA. So this is ABDA. So in this loop we'll be applying KVL. So if you apply KVL as you already studied in your basic electrical, I1 into R1 plus VBD minus I2 RX is equal to 0. If you follow one of the conventions, drop across the various branches will be equal to the source. So I1 R1 plus VBD minus I2 RX is equal to 0. Now, from the first equation already we know that VBD is equal to 0. So you will be left out with I1 R1 is equal to I2 into Rx. Now, this is nothing but equation number 2. I1 R1 is equal to I2 into Rx. Now let us have a look at the equivalent circuit here. I have just removed the galvanometer because the galvanometer, no current is going to flow through the galvanometer. I have removed the galvanometer and redrawn the same circuit containing R1, R2, Rx, Rs in the same positions connected to the source. Now here, since there is no galvanometer present here, I1 is same as I3 and I2 is same as I4. Here we have named I1, I3, I2 and I4. Since galvanometer is not present, Ig is 0, I1 is same as I3, you can write it as I1 itself. I2 is same as I4, we can write it as I2 itself. So from this, let us write down the expression for I1 and I2 from this circuit. So I1 is equal to E divided by R1 plus R2. See, both the branches are connected in parallel. So voltage is same in parallel. So I1 is equal to E by R1 plus R2. I2 is equal to E divided by R3 plus Rx. So this is equation number 3. Now we'll have to substitute equation number 3 in equation number 2. In equation 2, we have I1 R1 is equal to I2 Rx. In place of I1 and I2, I'm going to substitute E by R1 plus R2 and E by Rs plus Rx. So if I substitute that, I have E by R1 plus R2 into R1 is equal to E by Rs plus Rx into Rx. So E gets cancelled out. You are left out with R1 by R1 plus R2 is equal to Rx by Rs plus Rx, cross multiply. R1 Rs plus R1 Rx is equal to R1 Rx plus R2 Rx. So here R1 Rx gets cancelled out on both the sides. You are left out with R1 Rs is equal to R2 Rx. So product of opposite arms of the bridge are equal. This is the condition for bridge balance. So let us see the circuit once again. Whenever any Wheatstone bridge circuit or any bridge circuit for that matter is said to be balanced, product of opposite resistances should be equal. So this is the condition that we have derived. This is equally true for AC bridges also. Any bridge circuit, if you take, whenever the bridge is balanced, you can take it as product of opposite resistances are equal. So R1 Rs is equal to R2 Rx. So here from the circuit, we already know that Rs, R1 and R2 will be known to us. So knowing these three values, we can find the unknown resistance Rx. So this is called as bridge balance condition. And in the examination, sometimes they'll ask you to derive the same. So this is what happens whenever the bridge is said to be in balanced condition. And always there is a probability practically that the bridge will not be in balanced condition. Most of the time, as soon as you connect an unknown resistance, bridge will not be balanced. Bridge has to be balanced. So whenever there is an imbalance in the bridge, obviously current will flow through the galvanometer. So in that particular case, let us try to find the expression for the current flowing through the galvanometer. When the bridge is balanced, no current will flow through the galvanometer. But when the bridge is not balanced, current will flow. We'll have to find that current when the bridge is unbalanced. So for this purpose, I'm introducing Thevenin's theorem. In your electrical circuit analysis, you'll be studying in detail about what is Thevenin's theorem, and you'll be solving several problems on Thevenin's theorem. So here for this, I'll be using Thevenin's theorem. So let me introduce the theorem to you and apply the same for our Wheatstone bridge circuit. Let us go through the statement. Any active linear network with two terminals can be replaced by an equivalent voltage source in series with a resistance R, voltage being equal to open circuit voltage of the terminals and resistance being equal to equivalent resistance of the network between the terminals, with all voltage sources in the network replaced by their internal resistances. This is the statement of Thevenin's theorem. So just have a look at this diagram, circuit diagram below. So this is a sample network I have taken. You are having source voltage E, you are having R1, R2, R3 and R4, and then here you are having a load resistance, another resistance called as load resistance. So this theorem says that this network containing source and several other elements, passive elements, can be replaced by a single source and a single impedance or single resistance, as you can say, and then connect this R load so that you can find the current flowing in this loop. See, if this is if you are having the actual circuit has R1, R2, R3, R4, circuit tends to be a bit complicated. Since the circuit is complicated, you'll have to use node analysis or mesh analysis, and this is a simple circuit. If it is more complicated with more number of branches, it will be tedious. So we'll be using this Thevenin's theorem in order to simplify it. So in using this Thevenin's theorem, the source voltage with several other resistances can be replaced by single voltage source and single resistance. If it is an AC circuit, it will be single impedance, so that the current can be found very easily. So let us see how to apply this, taking an example. So before that, I'll just go through the procedure for solving problems on Thevenin's theorem, and please be aware that I have written review here. Review in the sense, this is not a part of your syllabus. You don't have to study Thevenin's theorem or its application here in this subject. It is just for us to understand the derivation later on. That's why it is called as review content. So step 1, remove the element through which current flow needs to be found and consider the element endpoints as terminals. Next step, find the open circuit voltage across the terminals, which is VOC. Step number 3, to determine Thevenin's equivalent resistance or impedance, generally called as ZTH. Since it is DC, you can directly take it as RTH. For this, A, short all voltage sources, open all current sources in the network, and B, determine the equivalent resistance or equivalent impedance between the terminals. Step number 4, replace the network by VTH in series with RTH to determine and obtain Thevenin's equivalent network. So let us see how to use this Thevenin's theorem over here. So in this problem, find current flowing through 30 ohm resistor using Thevenin's theorem. This is a simple circuit. For understanding the application of Thevenin's theorem, I have just taken this. So through this 30 ohm resistance, the current flowing needs to be found. So if you have to find the current flowing through this 30 ohm resistance, let us follow the procedure. Step 1 says, remove the element through which current flow needs to be found. So through this 30 ohm, I am supposed to find the current. So I am going to remove this 30 ohm and consider the element endpoints as terminals. So I'll call these two ends where I have removed 30 ohm as terminals. They are terminal A and terminal B. So this is step 1. So in step 1, I have just removed 30 ohm resistance through which the current flow was needed to be found. Then step 2, find the open circuit voltage across the terminals. I have to find the voltage across this A and B. So let us see how to do that. So if you try to find the current flowing through this first loop here, I1 will be equal to, using Ohm's law, V divided by R. R is nothing but sum of the resistances. Since ends A and B are open, no current will flow through this 20 ohm. Current only is going to flow in the loop here. So this current will be equal to voltage divided by total resistance. So total resistance is 5 plus 10, which is 15. Voltage is 10. So 10 divided by 15 is nothing but the current. So this is what is I1. Then once I know I1, product of I1 and this particular resistance will give me voltage across this 10 ohms. See, since this A and B are open, voltage across A and B is same as voltage across this 10 ohm, since no current is going to flow in the open part of the circuit. So voltage across this 10 ohm will be current flowing through the 10 ohm multiplied by the resistance 10. So I1 multiplied by 10 will give me open circuit voltage VOC or VTH, which is I1 into 10. 10 by 15 multiplied by 10, which is 100 divided by 15, which is equal to 6.6 volts. In the next step, so this finishes step 2. So in step 2, we have found the open circuit voltage across the terminals. Step number 3, we have to find equivalence Thevenin resistance across the terminals. That means we are supposed to find the equivalent resistance across this terminal. So if you have to find equivalent resistance across the terminal, the rule says short all the voltage sources, open all the current sources in the network. In our network, we only have voltage source, we don't have current source. So I have shorted the voltage source. That is, I have replaced replaced the battery by a line. So here you can see there was a 10-volt source. This is just replaced by a line now, short circuit. So if you replace that by a line, connecting conductor, you are having 5 ohm, 20 ohm, 10 ohm, and now I am supposed to find the equivalent resistance here. So how do you find the equivalent resistance? 5 and 10 are connected in parallel. Then the combination equivalent resistance will be in series with this 20 ohm. So you very well know that whenever two resistors are connected in parallel, R1 R2 by R1 plus R2 will give you the equivalent resistance. So 5 into 10 divided by 5 plus 10. This will appear in series with 20 ohm. So 5 into 10 by 15 plus 20. So this will give me 23.33 ohms. You can calculate and check. Now, step number 4. Replace the network by VTH in series with ZTH to obtain the Thevenin's equivalent network, where VOC is nothing but VTH. So what I have to do? Replace the entire circuit by VTH in series with RTH. I have my VOC or VTH as 6.6 volts and the RTH value is 23.3, and now I bring in the 30 ohms that I had removed in step 1 back into the source. So this is what Thevenin's theorem says. So all the see, you can see here 10 volts, 5 ohms, 20 ohms and 10 ohms. This part of the circuit is just now replaced by 6.6 volts in series with 23.33 ohms resistance. Now in the last step, I am bringing in this 30 ohms which I had removed in step 1. Now it will be easy for me to calculate the current flowing through the loop. So current flowing through the loop will be VTH divided by RTH plus 30. That will give me 123 milliamperes, 0.123 amperes. So current I is nothing but VTH divided by sum of these two resistances, which will give me 123 milliamperes. So this is how you are going to use Thevenin's theorem to to calculate the current flowing through an unknown branch, current flowing through a branch when the circuit happens to be complicated. So let us try to apply the same in Wheatstone bridge circuit whenever there is a small imbalance in the bridge. Imbalance in the sense there is no current flow, so there is a current flowing through the galvanometer. So first, when to start with this derivation, let us assume the bridge is under balance condition. We have some equations to be written here. So whenever the bridge is under balanced condition, you know that Ig is equal to 0, Vb is equal to Vd. That is being written here. And bridge balance condition is product of opposite resistances are equal. R1, R3 equal to R2, R4. So R1, R3 is equal to R2, R4. In the previous derivation, I have taken different notations. Here I have taken R1, R2, R3, R4. There we had taken R1, R2, Rs, Rx. So notations can be changed, not a problem. Now here, for this particular expression, R1, R3 is equal to R2, R4, I'll be adding R1, R4 on both the sides. So if I add any term on both the sides mathematically, it does not make any difference. So now I'll take R1 as common factor here. I have R3 plus R4, and here I take R4 as common factor on the right side. I have R1 plus R2. So if I rewrite this, I have R1 divided by R1 plus R2 is equal to R4 divided by R3 plus R4. I'll call this as equation number 1. So let me just repeat. I have started with bridge balance condition, which is product of opposite resistances are equal. So R1, R3 is equal to R2, R4. I'm just adding R1, R4 on both the sides. So R1, R3 plus R1, R4 is equal to R2, R4 plus R1, R4. I have taken R1 as common factor in the LHS. So I'm left out with R3 plus R4. On the right side, I have taken R4 as common factor. I have R1 plus R2. Now if I rearrange this, I am bringing R1 plus R2 to the left side. I'm sending R3 plus R4 to the right side. So I have R1 by R1 plus R2 is equal to R4 by R3 plus R4. I'll call it as equation 1, which I'll be using later on. Now, There is a small imbalance introduced in the bridge circuit by including a small incremental resistance delta R with R4. So I have modified this particular circuit now in order to study the effect of imbalance. So I'm introducing delta R additionally along with R4. If I only had R4, the bridge was balanced. Since the resistance has changed here, there is an imbalance created in the circuit. So once there is an imbalance created in the circuit, Ig is not equal to 0. Now current flowing through the galvanometer is no more 0 because the bridge is imbalanced, and VBD is not equal to 0. Earlier the potential difference was 0. Now that is also not equal to 0. And VB is not equal to VD. Earlier VB was same as VD. Now VB is not equal to VD. Now I will be using this Thevenin's theorem that we have studied in order to find this uh, current flowing through the branches. So first, VBD is nothing but I see my intention here is to find the current flowing through the galvanometer. So if you compare the example that we have taken for Thevenin's theorem, in order to find the current flowing through a particular branch, first you need to remove that particular branch. The 30 ohm we had removed in that example. Here also, I have to find the current flowing through this galvanometer. So I'll be removing the galvanometer. So first step, I am removing the galvanometer and I'll be naming this as terminals. So already terminal name is given. So I'll call it as VBD. This VBD is nothing but your VOC. That is step number 1. Second step is my intention is to find the open circuit voltage across the terminals. That means I have to find the potential difference across these two terminals. So if I have to do that, I have to redraw the circuit, and this is how the circuit is being redrawn, where the terminals, the galvanometer is being removed, and this is how your circuit looks like as we have drawn earlier. Here you have R1, R2. I have named the terminals. You can just see here also in between AB I have R1, between BC I have R2, between AD I have R4 plus delta R, between CD I'm having R3, and I have the source voltage E. Now my intention is to find this VBD. So if I have to find this VBD, first I'll be applying Kirchhoff's voltage law, KVL. So if I apply KVL here, I1 R1 plus VBD minus I2 into R4 plus delta R is equal to 0. In this loop, I am applying KVL. So VBD is nothing but equal to I2 into R4 plus delta R minus I1 into R1. This is VBD. Similar to what we did in the previous derivation, I'll be writing an expression for I1 and I2 in terms of source voltage. So for that, I'll be using this circuit. As you know, I am going to consider I1 and I3 to be same here, and I2 is same as I4. So your I1 will be E divided by R1 plus R2, and I2 will be E divided by R3 plus R4 plus delta R. So if I use that here, I have R4 plus delta R as usual. In place of I2, I am writing E divided by R3 plus R4 plus delta R. And in the second expression, I have R1. In place of I1, I am writing E divided by R1 plus R2. So if I take E as the common factor, I am left out with R4 plus delta R divided by R3 plus R4 plus delta R minus R1 divided by R1 plus R2. Now I'm going to use equation number 1 in the above expression. Let us see what was equation number 1. Equation 1 was R1 by R1 plus R2 is equal to R4 by R3 plus R4. I'm going to use that here. So you can see that in place of R1 by R1 plus R2 over here, I'm going to write it as R4 by R3 plus R4. And I'm going to take LCM and simplify this. So after simplification, and some terms will get cancelled out, I'll be left out with E R3 delta R by R3 square plus R4 square plus R3 R4 plus R3 R4 plus delta R into R3 plus R4. You can just take the LCM and check. And then this can be written as E R3 delta R by R3 plus R4 whole square plus delta R into R3 plus R4. And then that's what A plus B whole square is A square plus B square plus 2AB. That's what's being done here. Then delta R being very small compared to R3 plus R4 whole square, it can be neglected because it's a very small value in comparison with those resistances, and above all we are adding them and taking the square, it will be a huge value. So delta R can be neglected. If you neglect that, you'll be left out with E R3 delta R divided by R3 plus R4 whole square. This is the potential difference between B and D. So we have completed step number 2 of Thevenin's theorem. Let me just go to that page. So Thevenin's theorem says find the open circuit voltage across the terminals, step 2. So in the first step, we have removed the galvanometer in that particular derivation where I have to find the current. Just try to compare, and I have called the terminals. There the terminals already there. And here in step 2, we had found the voltage VTH here. Same thing I have done now. I have found VBD. Next, step number 3 here, it says you have to find the Thevenin's equivalent resistance by shorting all the voltage sources, opening all the current sources. So in the problem also we had done the same. We had shorted this 10 volt source and we had found the resistance across these two terminals. Same thing we'll be doing here. So I have just redrawn the circuit in the other fashion to show you this. So you can see the location of the respective resistances are there between the same terminals. I've just reversed it. I have drawn it vertically. So the voltage source E, I have short circuited over here. No current source is there here. And then A and C has been shown here. So you can see between A and C, I had a source which I have replaced by a short circuit or a line. So AC, I have shown it outside here. So A and C, it is same if you connect it from outside or if you connect it from inside. So in the next diagram, you can see I have connected from inside. And then now I have to find the resistance between B and D. So it's very clear. R1 and R2 are in parallel. R3 and R4 plus delta are in parallel. So if you can take, this will become a single resistance. This also will become single resistance. Those two equivalent resistances will be in series. So when R1 and R2 are in parallel, the equivalent resistance is R1 R2 by R1 plus R2. Here R3 and R4 plus delta are in parallel. So R3 multiplied by R4 plus delta R divided by R3 plus R4 plus delta R. That will be the equivalent resistance. So both the equivalent resistances will appear in series. So sum of these two will give me equivalent resistance, which is nothing but RTH. Now what we have to do, as per the step number 4, replace the entire network by this VTH in series with ZTH or RTH. So what I have to do here, now you can see I have just written VTH and I have written RTH, and I have galvanometer over here. Galvanometer was the one that we had replaced. I have just written the galvanometer also contains a resistance, so I have written it as RG. Now the entire circuit, what you can see here, the bridge circuit is replaced by VTH in series with RTH, and then you are having galvanometer has been brought back by writing it as RG. So VTH, RTH, RG. Current flowing in this loop is nothing but IG, because current flowing through RG is IG. So IG is equal to, now it is becoming very easy, IG is equal to VTH by RTH plus RG, where your RTH is this expression and this is your VTH. Now let us consider a special case where the bridge has equal arms. Suppose if the bridge has, see, this ends the derivation, that is whenever the bridge is in unbalanced condition, current flowing through the galvanometer is VTH by RTH plus RG, where we had the expressions for VTH and RTH. Now a special case where bridge has equal arms. In case the bridge has equal arms, that is R1, R2, R3, R4 being equal to a single resistance R, then let us see what will happen to IG. So just take up the equation of VTH, which is E R3 delta R by R3 plus R4 whole square. Here, just R3, R4 should be equal to R. That's what you have to do. So E R delta R by 2R the whole square. That's what happens. See here, R3 into delta R will be R into delta R. Here you will be having R plus R, which will become 2R the whole square. So this will be ER delta R by 2R the whole square, which will be giving you ER delta R by 4R square. R gets cancelled. You'll have E delta R divided by 4R. And then coming to RTH. RTH, you can see here you have R1, R2 by R1 plus R2 plus R3 R4 by R2 plus R4. You just have to substitute R1 R2 R3 R4 equal to R. So here in the numerator it will become R square, here it will become 2R. So R square by 2R plus R square by 2R. So it will give you R square by 2R into 2. If you cancel, the equivalent resistance will be R. So your Ig will be VTH by RTH plus RG. So your VTH is nothing but E delta R divided by 4R that you can see here, divided by R plus RG, because the RTH is nothing but R and you are having RG which is replaced here. So this represents the special case when the bridge has equal arms.